So module 3, right? Module 3 basically has these 6 things that we have to look at, right? Design and use of thermometers in this already, right? We're just going to use different definitions for a few quantities. Thermal properties did that already. Heat transfer did that already in a way, right? Kinetic theory of gases, you did the intro into that. Thermodynamics, they never did that before. And mechanical properties, Hooke's law, you did that, right? So you have an intro to everything there except the first law of thermodynamics, right? Actually, this is the handout with all the things. Yes. Okay. This handout has 1 to 5, right? So I'll just send it back the next one. But my head drop now. But I'll just send you that after, right? So these are the 6 things that we're looking at, right? As I said, the only thing that brand new there is 5. Heat transfer a little bit different because we never did a formula or proper explanation of conduction. So we're doing that there. Kinetic theory of gases, you did most of it already. Thermal properties, you did that already, and have some new things in module 1. All right. So we started with thermodynamics, right? Sorry, with the design and use of thermometers, right? This is a real nice module. We should finish it hopefully during this period here, right? It's about 6 hours. We have it. 3 this week. We have 3 this week and 3 next week. So we should, if not complete it, right? Cover most of it, right? All right, let's begin. So I'll run through the first set of things that we know already. There is something new here. It's called a thermometric property, right? Technically, we've been using it. What has happened when you take a mercury in glass thermometer, right? And you place the mercury glass thermometer into a hot liquid. What has happened? The mercuries go up, right? But why? Why does the mercury go up for something hot and go down for something cooler? Why does that happen? What are reactions to that? Reacting to the heat or the lack of heat, right? So really and truly, when you heat the mercury expands. Because of that expansion, it will move up. When it cools, it will contract, it will move back down. Right? That is called a thermometric property. So a thermometric property is one that has these 3 main properties here. Right? It has the ability to vary with time. Of course, it is measurable and it behaves uniquely over a particular range, right? So it's something that we know already, but probably the first time we actually get that too. All right. So let's start here with the beginning. Thermometers. The temperature of a body is the degree of its hotness. Thus, temperature is a measure of how hot a body is. Thermometers are used to measure the temperature and they utilize a thermometric substance, right? A thermometric substance is something that we're talking about. Some of them have mercury, some of them have alcohol. What else? Gotta remember that particular one. You didn't spend much time with the top 5, but there is a next thermometer that you use, and I had a different thermometric property. One is alcohol, one is mercury, but there's a next one that you use. Has a wide range of temperatures. A what? A thermocouple. But what kind of values it gives you? Huh? Does it actually give you temperature readings? No. What it gives you? You have to work out the temperature, but it gives you something else. Anybody on any number? Huh? No, it's like galvanometer. So it'll give it current. So it'll give you a voltage reading and current reading. And then you take that and convert it into a temperature. Right? So the thermocouple doesn't actually give you a temperature reading per se, it gives you a voltage reading. And I'm going to show you how to take that voltage reading and get a temperature. Okay? Right, so this physical property is called the thermometric property of the substance. A good thermometric property. Wait, everybody have the handout, right? No. It's in the group. All right. Wait, Kalina, you didn't get the sign after you. Module 3. Second thing. Yeah, follow it down. Wait, no, I was second. That was good. All right. And you know, but I'm fancy that something. You'll say that when you open it. Hey, no. You'll say that. Let's send it back then. You got it? Right, yeah. So these are the three things. These are the three things here that define a thermometric property. It constantly, it varies continuously with temperature. It behaves uniquely over a range of temperatures, and most importantly, it can actually measure, right? So those are the three properties. Yeah, does that? So those are your three properties. Those who have the notes and you know you're not going to read it, just write that down now. Right? Just write down the key things that they go along because some of you are not going to open their handout. Look at it, those three things there. Thermometric properties, those are the three important things, right? Has to vary with temperature continuously and it has to be measurable, right? Those are the two most important things. That's why they chose mercury. Right, a little heat and you'll be able to measure the variation. Okay with that? Yeah. So that's the principle behind thermometric property, right? Let's take a look at a few examples. Yeah. Right. All right. So those are your three things, right? Below here we have some examples, right? Volume expansion of a liquid, the laboratory thermometer, and the clinical thermometer, right? Pressure change of a fixed mass, constant volume gas thermometer. Actually, I think there's a simulation. I'll show you this one, right? You'll recognize that constant volume. And which gas law has a constant volume? Which gas law has a constant volume? Huh? Pressure law, right? So basically, that thermometer operates on the principle of pressure law, right? It operates on the principle of pressure law. A change in pressure will give you a change in temperature. That's okay? So that constant volume gas thermometer, right? The thermometric property is the pressure change of a fixed mass of gas. So you're taking a fixed mass of gas, and based on how the pressure changes, you get a temperature reading. Okay? I'll show you how it looks just now. I don't think you guys ever saw that before. Thermocouple, you get a change in EMF. And resistance thermometer, well, we don't use that, but a resistance thermometer, the resistance will change. Okay? So the thermometric property is the resistance, but we take those four properties and we convert it into temperature reading. Okay? So for example, when you all had a thermometer, right? If you remember this from form 5, right? When you had a thermometer, initially the thermometer has no readings, right? That's okay? All you have is a little mercury down. How are you gonna get readings, Darian? The first time I see it, I don't mind. I actually did my touch you something. Yeah, Darian. So Darian, let's say I gave you a thermometer. Thermometer has mercury in it. How do we get those actual readings? Because initially it don't come in those markings, right? But you always have it. Right. What you do is you just take the thermometer, place the thermometer in pure melting ice, and you get it 0 mark. Then what? Above pure boiling water, and you get the temperature of steam, 100. So you get the 0 mark, you get the 100 mark, and then you divide it up. That's okay? And then you can take the thermometer now here and put the thermometer anyway, and get a temperature between 0 and 100. That's okay? So there's a formula that does the same thing here. All right? That formula is called the empirical formula, and I'll show you that now. Right? And the formula basically it does the same thing for the thermocouple, it does the same thing for the constant volume gas thermometer, and it does the same thing for the resistance thermometer. That's okay? It gives you standard values 0 and 100, and then finds the values in between. Okay with that? So technically, in the clinical thermometer, you're really finding how much your liquid has expanded, right? And then you're converting that to temperature. Maybe which one? All of that. But in this one here, clinical thermometer, you basically observing how much the liquid expands, and then it converting that into temperature, right? But the thermometer has markings for you, so that's why it's easy to read it all. Thermocouple doesn't, right? Are you okay with that? You'll follow what thermometric property is, right? Let's take a look at one of them. Let's take a look at the thermocouple. Hold on, huh? Something. I understand. All right, let's take a look at this here. Hold on, thermocouple. All right, there's one in a lot. That's a play with the formula. Started by and show which one up. Let's try this one out. All right now. Okay. Oh yeah, I want to show. Yeah, inside. Using that wrong question. And so if you look here, right? Watch this here. I'm gonna show you how it this one is covered in black. Alright, watch here. Right is not the best image here, right? But right? So if you look here, here's what it is, right? Here you have a liquid of unknown temperature, right? Here you have liquid of unknown temperature, and then we have gas inside here, gas in here that trapped in here, right? And then what you have, I don't know if you all remember this on part 5. Remember the U-shaped manometer, right? The U-shaped manometer could be used to find the pressure. So basically, here's what happened, right? The pressure inside the gas here, is basically the pressure acting on this liquid. Right here, right? If you all remember how the manometer works, the pressure emitted here, remember pressure is the same at the same depth. Remember that? Pressure is the same at the same depth. So therefore, the pressure of the gas here is equal to the pressure of the liquid here plus the pressure of the atmosphere on top here. Remember that? So basically, pressure of the gas is equal to pressure of the atmosphere plus the pressure of the liquid. Right? So the way this works is that we try to find the pressure of the gas by adding atmosphere and pressure of the liquid. This liquid here. Anybody remember how to find out? Let's find out. Density of the liquid most likely is mercury by gravity by that height. Right? When you multiply this value and you add it to this, you'll be able to get the pressure of the gas. Right? And then we use the empirical formula and find the temperature. All right? Or the next option, if you know the temperature, what's the next option? See, we remember with that point by code. Suppose you know this temperature. Let's call it T1. You know T1 and you find what P1 is. How you can find the temperature of an unknown substance T2 now? Change the liquid. Which one is that? So you get the pressure low, right? Yeah. P1 on T1 is equal to P21. Right? So that's one of the ways that we can find an unknown temperature using the constant volume gas thermometer. Okay with that? Yeah. So that's the way it works, and you see how complicated it is to kind of set up, right? So that's one of the reasons why we don't really use it in the lab. But if you have the Charles law, the pressure law experiment set up, you can do it. All right. That's basically how it works. I believe the website I used to use like a lock it up here. I don't subscribe and pay for it. All right. So that's the way the thermometers work, right? Now, how can we use it? So watch this here. Last thing, and I'll give you a quick, right? Hook you up one. We'll stop now. Stop now. Right. So everybody okay with thermometric property and how the thermocouple and the constant volume gas thermometer work? Yeah. Right. These are some fixed points that we have to learn. You should know the first two. Anybody remember the exact definition of the first two? Ice point and steam point. Yeah, better explanation now. Ice point, yes, ice point is 0 degrees Celsius. But what is the full definition? Ice, forget one word, pure melting ice. Because remember, ice could be at different temperature, but when it's melting, it has 0. Okay? So the temperature of pure melting ice and steam point is what? The temperature of pure melting steam. Temperature of steam above pure boiling water, right? Again, the water must be at the boiling point and then you measure steam. Triple point. Anybody ever heard about triple point? Can people? Diane, yeah. Huh? What's triple point? Huh? Yes, technically all three in equilibrium. Right? So there is a particular temperature where solid, liquid, and vapor exist. And it's sort of observable above a pond. Like when a pond is frozen, you might be able to see at a particular point, particular temperature, water, ice, and a little bit of vapor above it. At that particular point, that's called a triple point. Okay, when all three exist. Right? So the ice point definition there, we know it's 0 degrees Celsius. Steam point definition there. Right, but triple point, the triple point of water is the unique temperature at which pure ice, pure water, and pure water vapor can exist together in equilibrium. All right, we'll send me here and that's to write it down. What's the value? 0.01. Triple point. So what is triple point? Right? Again, do write the value in degrees, write the value in Kelvin, right? What is triple point? What is triple point in Kelvin? 273.01. But then please try those 6 months because it won't work, right? With working. Those who have the answers and with working.
I promise.
Right. So one thing you will notice, well, I didn't really bottom of the handout, right? But we don't use 273 anymore, right? To convert degrees. Kelvin, we use 273.15. Alright? 273.15. So to convert from degrees Celsius, I think I have it equal now. Can I get it? To convert from degrees Celsius to Kelvin, right? Add 273.15, right? No longer 273, although you get it wrong, right? Right, mate? Yeah, we have that. 7.15. Triple point, yeah, triple point in Kelvin. 273.16. It's triple point, right? Fixed triple point is 273.16. Right? One thing you'll notice that triple point can only occur at 6,611. Right? 611.2 pascals is the only pressure that triple point would happen on. Okay? So it's you don't really observe it so easily. Right? There's a very small pressure right occur. Right, so make a note that we would be using 270.15 from now on, right? For any conversion. 273.15. Right, we'll do thermodynamics scale graph. Right, so we have two scales that we have to learn to use. We have the Celsius scale and the thermodynamic scale. All right, we will do thermodynamic today. Very simple, right? So an interval of Kelvin is defined as being 1 over 273.16 of the temperature of the triple point of water as measured on the thermodynamic scale. So all that's saying is this. What? What? So all that's saying is this. If you want to get temperature in Kelvin, we need to use something called the thermodynamic scale. Right? The thermodynamic scale is pressure triple point. Sorry, pressure unknown temperature divided by pressure at triple point multiplied by 273.16. How we getting those values? So number one, here's how we do it. We taking the unknown temperature, let's call that theta, and we finding the pressure. So let's say we're using the same constant volume gas thermometer, right? So we finding the pressure at an unknown temperature. Then do it again at triple points. And we find pressure at triple point. To find the temperature of the unknown gas, unknown liquid, sorry, all we're doing is taking this pressure divided by this pressure and multiplied by 273.16. Right? And the reason for that is that 1 Kelvin is 1 over 273.16 of our temperature at triple point. So what you really have to understand is this. If you have to find temperature in Kelvin, that's the relationship that you're using. You have to find the pressure at the unknown temperature, pressure at triple point, and multiply it by 273.1. That's all. And that scale is called a thermodynamic scale, or sometimes you might see Kelvin scale. The reason it's called Kelvin scale is because they're giving it temperature in Kelvin. Okay, just head up thermodynamic scale and write it. Head up thermodynamic scale and write it. Thermodynamic scale. Thermodynamic scale. Right? Write the formula and just put note that these temperatures are always in Kelvin. Note that these temperatures are always in Kelvin. Right, so you would recognize that this scale just using pressure, right, at unknown temperature and pressure and triple point has nothing to do with any thermometric properties, right? Right. One little question and then I get everything. Right, so remember, yeah, just done. Thermodynamic scale of temperature is totally independent of properties of any particular substance, right? And it's therefore an absolute scale. So it doesn't have anything to do with thermometric properties like this. Right, just one question and we're done. Do number 3 up, please. The answer might be wrong, right? So let's check it and see. Try to find the temperature of boiling water. So try to find the boiling point of the unknown liquid.
This is the same.
Oh yeah, work out number 3 there. We just run into our summary module 1 then. This is all later the trade exam all over. Now? Oh. That comes up. To make it. Huh? Yeah, we can make it something. That may be Yeah. Oh, yeah. Finish it.
The answer is 369.2. Yeah.
Same thing? For the show?
Yeah.
No, that's wrong. Check it back. No, you wrong, never error there. Right? What's the formula we going to use?
T is equal to PT over PTR by
Right.
7.
Pressure unknown temperature divided by pressure triple point by how much? 273.16. Try it there. So which pressure is the pressure triple point? 1.937 by 10 to the 4. And the pressure at the boiling point is here 2.618 by 10 to the 4. And then multiply that by 273.16. Work it out, you should get it.
I think you should answer 0.
Oh, I didn't work it out. Right. Right. Oh, get up?
Yeah.
Okay. So again, you only use this formula when they give you thresholds and when they ask the temperature in Kelvin. Okay. The one that we're going to focus on tomorrow is the one that you will see in past papers a little bit more. Oh, you know what I mean? Next slide. Next slide. All right.